As one of the few African nations to break free from the shadow of poverty and food insecurity, South Africa has built a modern agricultural industry worth more than $15 billion, exporting millions of tons of fruit, livestock products, grains, and wine every year. So what has made South African agriculture different from the rest of Africa? Despite being located at the southern tip of the world's poorest continent, South Africa chose not to rely on the unpredictability of nature. Instead, it transformed its fertile valleys, rare Mediterranean climate, advanced irrigation systems, and strategic seaports into a large-scale agricultural powerhouse. Today, join Agriculture Insight as we explore one of the most advanced agricultural production systems in Africa, where farmers not only feed more than 60 million people at home, but also supply South African agricultural products to some of the most demanding markets around the world. Let's get started. At our first stop, we arrive in the Western Cape, a region with a harsh climate, yet home to some of the most productive grape valleys in the world. These vineyards generate more than $730 million in value each year and help South African grapes reach markets across the globe. Unlike the lush green vineyards of France or Italy, South African grapes are grown in a semi-arid landscape where summer temperatures can exceed 45 degrees Celsius. Rainfall is scarce and the ground often cracks under the intense sun that shines for most of the year. To farm under such challenging conditions, grapevines are trained on tall steel trellises that provide more even sunlight exposure and better airflow. Meanwhile, water from the Orange River is delivered directly to each vine through a drip irrigation system. Throughout the growing process, farmers continuously monitor the brix level, fruit size, and development of each grape cluster. Using specialized tools to measure sugar content and ripeness, they often cut sample grapes to check the internal quality. This helps them adjust care practices and determine the most ideal harvest time. After about 2 to 3 years of care, once the vines have reached stable production and the grape clusters have achieved standard size, the vineyards officially enter the harvest season. In South Africa, export grapes cannot be harvested like mass-market fruit, because long-distance shipping requires the grapes to maintain their freshness, appearance, and storage quality after weeks of refrigerated transport. As a result, machinery is largely excluded from this stage, and the selection process is carried out by hand directly on the vine. Workers carefully select each cluster based on sugar content, skin color, firmness, and stem attachment. They then use sharp pruning shears to gently cut the main stem, minimizing vibration that could remove the grape's natural protective bloom. Immediately afterward, any small, cracked, soft, or unevenly colored grapes are removed in the vineyard. Each cluster is then placed into shallow trays in a fixed orientation to reduce contact and prevent damage throughout the journey to export markets. After being harvested, the grape clusters are quickly gathered and transported along long routes through the arid landscape to packing facilities. There they undergo sorting and trimming, with any grapes that fail to meet quality standards removed. The remaining fruit is then packed under strictly controlled conditions to preserve maximum freshness. South African grapes are highly valued in international markets for their firm texture, crisp skin, delicate sweetness, and excellent ability to stay fresh during long-distance export. Their greatest strength lies in their consistent quality, attractive appearance, and durability, allowing them to compete directly with grapes from Chile, Peru, and the United States. If rice dominates Asia and wheat defines Western agriculture, then in Africa, corn is the true king of staple crops. Leading the way is South Africa, producing more than 14 million tons of corn each year and helping feed millions of people across the region. Here, around 3 million hectares of land are dedicated to corn, more than any other crop in South Africa. White corn accounts for more than 50% of production and is mainly used for human food, while the rest is yellow corn, used for animal feed and food processing industries. However, prolonged drought, unpredictable rainfall, and the growing threat of climate change have created major challenges for South Africa's corn industry. South African farmers lead Africa in mechanized corn harvesting. Compared with Malawi, Mozambique, or Zambia, where many smallholders still harvest ears by hand and shell kernels with family labor, South Africa uses giant combine harvesters such as John Deere, Case IH, and New Holland, imported mainly from the United States and Europe, capable of harvesting up to 40 hectares per day. This increases harvest speed dozens of times over, while sharply reducing manual labor under extreme heat, dust, and harsh weather. After harvest, the corn is transported by truck to collection points, weighed on electronic scales to determine output, and then unloaded into receiving pits. From there, conveyor belts and augers move the kernels into temporary storage facilities covered with sealed tarps, protecting tens of thousands of tons of corn before processing or sale. Leaving behind the vast cornfields, we now head to South Africa's Limpopo province, where macadamia nuts smaller than a fingertip are driving an industry worth more than $1 billion and turning this region into the macadamia capital of Africa. Across macadamia farms spanning hundreds of hectares, self-propelled macadamia harvesters become powerful assistants for South African farmers during each peak harvest season. After the macadamia nuts fall to the ground, rotating rubber brush rollers continuously sweep them into the machine. Inside, a high-powered air fan helps separate dry leaves, dust, and other light impurities before the nuts are carried into the storage compartment. Depending on the size and condition of the orchard, one machine can collect around 10 to 30 tons per day, many times faster than manual labor, before the nuts are transferred onto transport vehicles and taken out of the orchard. From there, the macadamia nuts are taken straight to processing factories, where the true value of this premium crop begins to be determined. After cleaning and sorting, the nuts are transferred into temperature-controlled drying silos for about 7 to 10 days to gradually reduce moisture. If they are dried too quickly, the oil-rich kernels inside can easily crack, causing the nuts to lose their crisp texture, natural buttery flavor, and market value. Once they meet the required standard, the macadamia nuts move on to the cracking line. The pressure rollers are adjusted with extreme precision, applying just enough force to break the hard shell while keeping the kernel as intact as possible. It is this high rate of beautiful whole kernels, rich, buttery taste, clean crunch, and high oil content that allows South African macadamias to sell for far higher prices than many ordinary nuts. Finally, the kernels are inspected, graded by size, packaged, and exported to premium markets around the world. When people think of South Africa, they do not only picture open fields or dry landscapes, but also massive cattle cities, where hundreds of thousands of cattle are fattened at the same time, helping create a beef industry worth around $5 billion each year. Compared with beef powerhouses like Brazil or Argentina, where cattle can rely on vast, nutrient-rich grasslands for longer periods, South Africa must plan more carefully because of its dry climate, unpredictable rainfall, and seasonal changes in pasture availability. Popular cattle breeds such as Bonsmara, Brahman, Guni, and Afrikaner are favored for their strong heat tolerance, ability to adapt to dry pastures, and stable weight gain under South Africa's harsh conditions. That is why, when calves reach around 7 to 12 months old, or about 200 to 250 kilograms, they are moved into feedlots as the final finishing stage. At large feedlots in South Africa, cattle feed is prepared in huge quantities, mainly from corn silage, hay, silage, and energy-rich agricultural byproducts. After harvesting, whole crop corn or forage grasses are chopped, tightly compacted, and formed into massive silage bales. These bales are sealed with multiple layers of plastic film to create an anaerobic environment, allowing natural fermentation to take place and preserving nutrients for months. They are then gathered into large storage yards before being sent to the ration mixing area, becoming an important year-round feed source for finishing cattle. During the first 6 months, calves mainly continue nursing from their mothers while beginning to graze in the fields. By the 7th month, they are moved into feedlots to enter the final finishing stage. Each day, one animal can consume around 8 to 12 kilograms of dry matter, depending on its weight and stage of growth. At feeding time, silage bales, hay, ground corn, protein, and minerals are loaded into a TMR feed mixer. The machine mixes the ration evenly while moving along the pens, distributing the feed directly into the troughs for the cattle. After months of grazing and finishing, cattle that meet market standards are guided through handling lanes and loaded onto specialized transport trucks. From there, they begin their final journey to meat processing plants, which can receive thousands of cattle each day from farms and feedlots across South Africa. From South Africa's semi-arid regions, Boer goats have reached more than 100 countries and become one of the world's most sought-after meat goat breeds, with high-quality breeding animals selling for around $2,000 to $5,000 each. Unlike many goat breeds that depend on abundant feed, Boer goats thrive in South Africa's dry landscapes, where the harsher the conditions become, the more impressive their survival ability and weight gain appear. In South Africa, Boer goats are usually raised on large farms stretching across semi-arid regions. During the first weeks of life, kids mainly nurse from their mothers to strengthen their immune systems and develop their bone structure. Once they reach around 15 to 20 kilograms, they begin adapting to hay, shrub leaves, ground corn, and protein-rich supplements. What made Boer goats famous is not a special diet, but their ability to convert rough forage into muscle very efficiently. With proper care, young goats can reach 30 to 40 kilograms in 4 to 6 months, while mature goats tolerate harsh conditions well and commonly produce twins. As a result, Boer has become a valuable meat goat breed in South Africa, often set for processing after 8 to 12 months, producing firm, lean meat with a rich but not overly strong flavor. There was a time when South African ostrich feathers were so highly prized by Europe's upper class that they transformed Oudtshoorn from a remote farming settlement into one of the wealthiest regions in the area. More than a century later, this giant bird remains a unique symbol of South Africa, supporting an industry worth around $110 million each year. Across the dry, semi-arid landscapes, the journey of every ostrich begins with a courtship display on the sand. The male spreads its wings, lowers its body, and swings its neck to attract a mate. After mating, the female usually begins laying eggs after about 1 to 2 weeks, producing around 40 to 60 eggs during each breeding season. Ostrich eggs are the largest bird eggs in the world, weighing about 1.2 to 1.8 kilograms each, with a thick, hard shell strong enough to withstand great pressure. On farms, the eggs are collected daily and placed into specialized incubation systems to control temperature and humidity while improving hatch rates. The chicks are then raised in brooding facilities where temperature, nutrition, and health are carefully managed. As they grow, they transition to a diet of ground grains, young grasses, minerals, and protein-rich feed. In just about 1 year, many individuals grow to more than 2 meters tall and weigh over 100 kilograms, becoming the largest living birds on Earth. But size is not the most remarkable thing about ostriches. They can run at speeds of up to 70 kilometers per hour, so fast that many international visitors travel to Oudtshoorn just to watch these giant birds sprint across sandy tracks and experience ostrich riding, the unique attraction that has become one of South Africa's most distinctive tourism experiences. Yet the value of ostriches extends far beyond tourism because almost every part of the bird can generate income. Ostrich meat is highly valued for being lean and rich in protein, while eggs weighing up to 1.5 kilograms can be transformed into decorative lamps, souvenirs, and works of art after use, with some pieces selling for hundreds to more than $1,000 each. For more than half a century since the wave of decolonization, Africa has always possessed a unique paradox. With nearly 60% of the world's uncultivated arable land and the fastest-growing young population on the planet, Africa has long been regarded as one of the regions with the greatest development potential in the world. In addition, the continent sits atop a resource base worth trillions of dollars, from gold, diamonds, and oil and gas, to cobalt, copper, and uranium, resources that play a critical role in the technology, energy, and industrial race of the 21st century. But Africa's greatest advantage is also its most critical weakness. Because for most people, the most important asset does not lie deep underground, but directly on its surface: land. The Sahara Desert stretches across more than 9 million square kilometers, dividing the continent from east to west, while many areas in the Sahel Belt continuously face drought, erosion, and land degradation. Agricultural productivity declines, people's incomes fall with it, and the cycle of poverty continues to spread like a vicious loop etched across generations. As a result, while much of the world is gradually escaping extreme poverty, Sub-Saharan Africa is accounting for an increasingly larger share of the world's poor population. However, instead of allowing the desert to continue determining its future, the continent has begun rewriting its destiny through an entirely different approach. From Senegal in the west to Ethiopia in the east, millions of people have begun implementing a solution that seems remarkably simple: digging small half-moon pits across barren lands. At first glance, they appear to be nothing more than scars in the middle of the desert. But from these tiny structures, millions of hectares of degraded land have been restored, millions of tons of food are produced every year, and the Great Green Wall has gradually taken shape. It is an effort to protect the productive foundation of an entire continent, as well as an ambition to narrow the development gap between Africa and the rest of the world. And to understand how African farmers and engineers have been able to transform barren lands into fertile fields, we must begin with the greatest enemy of African agriculture: water scarcity. The biggest mistake when looking at the Sahara is assuming that there is no water here. In reality, in many parts of the Sahel, annual rainfall is still sufficient to support agricultural activity on a certain scale. The problem is that most of that water does not remain long enough for crops to use it. After years of drought, overgrazing, and erosion, the topsoil gradually becomes hard and compacted. When brief rainstorms arrive, instead of soaking into the ground, most of the water quickly runs off across the surface and disappears. People may witness heavy rains lasting for hours, but just a few days later, the land returns to its barren state as if no water had ever appeared. This is also why many previous greening efforts failed to achieve the expected results. Since the 1970s, hundreds of millions of trees have been planted across the Sahel Belt to halt the expansion of the Sahara. But unlike the successes China achieved with the Green Great Wall along the edge of the Gobi Desert, most young trees in the Sahel could not survive beyond a few rainy seasons. Because the biggest problem was not the absence of rain, but the inability to retain water when rain arrived. And it was from this challenge that local farmers developed a solution so simple, it seems almost unbelievable. Instead of starting with trees, they started with holes. However, building half-moon pits is not simply a matter of digging holes. The first step is to accurately identify areas that have become degraded but still retain the potential for restoration. After selecting a suitable site, people mark thousands of positions using ropes, wooden stakes, or simple measuring tools. The pits are not dug randomly, but are arranged in multiple parallel rows running along the contour lines of the terrain. This design helps slow surface runoff across the entire slope, rather than at only a few isolated points. Only after that stage is completed does the digging begin. Essentially, half-moon pits are shallow depressions excavated directly into the soil in a curved shape with the opening facing upstream toward the direction of water flow when rainfall occurs. Each pit is typically only 20 to 40 centimeters deep and averages about 5 meters in width. Farmers use hoes or shovels to excavate the soil, then pile the removed earth into a small embankment on the rear side. At first glance, they appear to be nothing more than simple holes in the ground. But when thousands of pits are connected across the same slope, they begin to function as a massive rainwater harvesting system. When the rainy season arrives, surface runoff is slowed instead of rushing downhill. Water, sediment, and nutrients are trapped inside the pits rather than continuing to be washed away. Because most of the work is carried out entirely by hand, half-moon pits cost far less to implement than irrigation systems, dams, or large-scale water infrastructure projects. Viewed from above, the half-moon pits form countless smiles of the desert, stretching all the way to the horizon. Once water, sediment, and nutrients have been retained, only one final element remains: the first seeds. After the first rains fill the half-moon pits, local people begin planting food crops, forage grasses, and native species with high drought tolerance. Depending on the region, these may include millet, sorghum, cowpeas, or tree species such as acacia and African eucalyptus. After only a few rainy seasons, the difference becomes clear. While the surrounding lands remain barren and nutrient-poor, the half-moon pits begin to turn into small oases that retain moisture for significantly longer after each rainfall. This gives young plants a crucial survival advantage. Plant roots have more time to develop before the dry season returns. At the same time, the sediment and organic matter inside the pits continuously improve soil quality year after year. As vegetation grows, a self-sustaining ecosystem begins to take shape. Plant roots help stabilize the soil. Leaves cover the surface and reduce the rate of water evaporation. Organic matter from fallen leaves continues to be added to the soil, further improving its moisture retention capacity. From this point on, the half-moon pits do more than just retain water. They create the first conditions for nature to restore itself. The creativity of African farmers and engineers does not stop with half-moon pits. To restore larger areas, the people of the Sahel also use another simple technique: stone bunds. Instead of digging thousands of individual pits, they collect stones from nearby areas and arrange them into long lines running along the contour lines of the slope. Each stone bund is typically only 20 to 30 centimeters high, but can extend for hundreds of meters. Over time, this structure helps slow the flow of rainwater, allowing the soil layers behind the stone bunds to gradually become deeper and more fertile. But even when water is retained on the surface, one important question still remains: how can water supplies be maintained throughout the dry season, which lasts for many months? The answer comes from a structure that appears even simpler: sand dams. At their core, they operate much like the dams built by beavers, often referred to as nature's ecological engineers. Instead of trying to stop water with massive structures, both simply slow the flow long enough for water to be retained within the ecosystem. Along many seasonal streams in the Sahel, local communities build low concrete dams across streambeds. When the rainy season arrives, water continues to flow through the structure. However, sand and heavier sediment layers are trapped behind the dam. Millions of liters of water are stored within the sand layers, where they are largely protected from evaporation, providing a reliable water supply for household use, livestock, and agricultural production, for many months after the rainy season has ended. As a result, sand dams have become one of the most successful water management solutions in East Africa. Kenya alone has now built more than 1,000 sand dams, while Ethiopia, Tanzania, and Zimbabwe are also implementing numerous similar projects. Today, sand dams are regarded as one of the lowest cost, most durable, and most scalable water harvesting technologies for arid regions around the world. Each half-moon pit restores only a few square meters of land. Each stone bund protects only a portion of a hillside, and each sand dam supplies water to only one local community. But when these solutions are scaled across a corridor stretching more than 8,000 kilometers from Senegal to Djibouti, they become the foundation of a continent-wide ambition, the Great Green Wall. Over time, millions of small oases begin to expand and connect with one another. Lands that had been abandoned for years gradually see the return of grasslands, shrubs, and new cultivated fields. By 2026, approximately 300,000 square kilometers of degraded land had been restored across the Sahel region, making the Great Green Wall one of the largest ecosystem restoration programs in modern history. However, trees are only truly protected when they generate economic value. And one of the most valuable links in this new economy comes from gum arabic, a prime example of how the Great Green Wall is transforming land restoration into a trillion-dollar global supply chain. Gum arabic has been harvested across Sudan, Chad, and Senegal for centuries. But as millions of acacia trees take root across restored landscapes, the Great Green Wall is helping drive the industry into a new phase of large-scale expansion. After approximately 5 to 7 years of growth, acacia trees begin producing harvestable yields. During the dry season, people use knives to make small cuts in the trunks and branches. As a self-protection mechanism, the trees secrete a transparent resin that gradually dries into amber-colored crystals. About 2 to 3 weeks later, these resin lumps are collected by hand, cleaned, and transported to collection centers before being exported. What makes gum arabic special is its nearly irreplaceable role in the food industry. It functions as a natural stabilizer and emulsifier, helping maintain the texture and quality of thousands of products, from soft drinks and confectionery to pharmaceuticals and cosmetics. The consistent demand from these industries has helped high-quality gum arabic typically trade at prices ranging from around $2,000 to more than $4,000 per ton on international markets. For many households, gum arabic accounts for as much as 15% to 40% of annual income, making it one of the few practical pathways to improving livelihoods and escaping poverty. For many years, Sudan supplied approximately 80% of the global gum arabic supply, making the Sahel a strategic link in the supply chains of some of the world's largest food and beverage corporations, such as Coca-Cola, PepsiCo, and Nestlé. More importantly, every kilogram of gum arabic sold gives local people an additional incentive to protect trees rather than exploit or cut them down. As a result, the Great Green Wall is not only restoring land, it is turning trees into an economic asset capable of sustaining the restoration process itself. Gum arabic is just one small piece of a much larger picture, the revival of the Sahel belt. Ahead still lie millions of hectares of land waiting to be restored, while climate change, population growth, and resource pressures continue to create new challenges. If successful, this could be the first time in modern history that an entire continent uses ecosystem restoration as a large-scale economic development strategy. In your opinion, can the Great Green Wall become Africa's economic turning point in the 21st century? Or are institutional, political, and conflict-related issues the greatest barriers that trees cannot solve? As the land comes back to life, areas once threatened by desertification are being transformed into fertile farmland, producing millions of tons of food and agricultural products across Africa every year. Nourished by the Nile for more than 5,000 years, Egypt, the cradle of one of the world's greatest agricultural civilizations, is gradually reaching the limits of its own survival. The country's greatest paradox is that it possesses nearly 1 million square kilometers of territory, roughly equivalent to the combined area of France and Germany, yet less than 4% of that land is actually suitable for cultivation. However, the problem is not simply the lack of farmland. The problem is that it is almost impossible to expand. While the population of this Muslim-majority nation continues to grow by around 1 million people each year, the amount of arable land has remained virtually unchanged, an inevitable limitation. Worse still, about 25,000 hectares of agricultural land disappear every year due to urbanization. As a result, nearly 60% of Egypt's food demand depends on external supplies, making the country one of the world's largest wheat importers. Not only is Egypt constrained by its harsh deserts, but it also faces a critical vulnerability. The entire nation depends almost entirely on a single river. Approximately 97% of Egypt's freshwater supply comes from the Nile, a river stretching more than 600 kilometers across 11 countries. Yet most of its flow originates from the Ethiopian highlands, where the Grand Ethiopian Renaissance Dam has raised concerns about the future of Egypt's water supply. This means that the fate of more than 110 million people depends on a river whose flow is not entirely under their control. While many see only hot, barren sand, Egypt sees a vast reserve of untapped land. If water can be delivered there, these areas could become a strategic space for absorbing population pressure, expanding food production, and strengthening national security. As a result, Egypt began constructing an unprecedented irrigation system, collecting, treating, and redistributing million cubic meters of water every day to transform nearly 1 million hectares of the Sahara into a new food-producing region for the 21st century. However, this is not the first time Egypt has attempted to turn the desert into farmland. Decades ago, the country placed enormous hopes on Toshka, a project celebrated as a miracle in the desert, yet its actual results fell far short of initial expectations. So what makes Egypt believe that this time will be different? And to understand how Egypt could create a second Nile Delta in the heart of the Sahara, we must begin with what seems like an impossible challenge: transporting millions of cubic meters of water across the desert. In 2021, the New Delta project was officially launched. More than 12,000 workers and hundreds of heavy machines operated almost around the clock, transforming the area into a massive construction site in the middle of a sea of sand. The first step was stabilizing the terrain, as building on constantly shifting sand presents a major challenge. Across a landscape where sand continuously moves under the influence of wind and temperature, hundreds of bulldozers worked relentlessly to level the ground, remove large sand dunes, and reshape the entire desert surface. Once the site had been prepared, canal excavation began. The canal was designed to be about 45 meters wide and 7 meters deep, capable of transporting enormous volumes of water using gravity alone. At the same time, the accuracy of the entire route was strictly controlled. The longitudinal slope was adjusted with an error margin of only about 2.5 centimeters per 30 meters, a level of precision that is almost unimaginable for a project stretching hundreds of kilometers. Amid temperatures exceeding 50 degrees Celsius, the entire construction site operated like a giant machine, constantly moving across an endless sea of sand. Excavating the canal was only half the battle. The bigger challenge was moving billions of liters of water across more than 100 kilometers of desert while minimizing losses along the way. As a result, preventing water loss became one of the most important objectives of the entire project. After the canal bed was stabilized, a layer of fine sand, approximately 5 centimeters thick, was evenly spread to create a cushioning surface before 10 to 12 centimeter thick concrete slabs were poured in standardized sections. Between the concrete slabs, expansion joints were sealed with hot bitumen to prevent leakage and allow the structure to expand and contract under the desert's extreme temperature fluctuations, where temperatures can range from around 10 degrees Celsius at night to over 50 degrees Celsius during the day. Upon completion, more than 124 kilometers of canal had been reinforced and waterproofed, creating one of the largest water conveyance systems in North Africa. Once the canal had been fully reinforced and waterproofed, the next step was the art of flow control. Along the canal route, intermediate regulating reservoirs covering approximately 2 hectares each were constructed to absorb flow fluctuations and maintain a stable water supply. But a giant canal alone could not support nearly 1 million hectares of farmland. Water still had to be delivered with precision to fields scattered across the desert. From the main canal, pipelines ranging from 1.5 to 3 meters in diameter are installed to deliver water to new agricultural areas in the desert. Most of the system is buried underground to minimize evaporation losses, while high-capacity pumping stations and automated control systems continuously regulate the flow, ensuring a stable water supply throughout the region. But what makes the new delta fundamentally different from Toshka and many desert reclamation projects before it is not the scale of the project. It is the water behind it. Most of the water comes from the agricultural drainage system in the Nile Delta, where it is collected and treated at massive facilities such as Al Hammam before being pumped back into the desert. When the first control gates were opened, water began flowing through the newly completed network of canals and pipelines. Every day, more than 7.5 million cubic meters of water move through this system, making the new delta one of the largest water redistribution networks ever built in North Africa. From this point forward, Egypt is not simply bringing water into the desert, it is recycling its entire irrigation system to create a new food production engine for the 21st century. As the first flows of water began moving through the new network of canals and pipelines, vast green oases gradually emerged across the heart of the Sahara. Spanning nearly 924,000 hectares of newly cultivated land, these remote desert regions are becoming one of the agricultural hubs contributing more than 15 million tons of agricultural products each year. For many Egyptian farmers, this is the first time they have watched the desert give way to green fields. One of the new delta's most important objectives is reducing Egypt's dependence on imported food. Wheat, the country's staple crop, sits at the center of that strategy. Egypt still imports around 10 to 12 million tons of wheat annually, equivalent to nearly 60% of domestic consumption. As harvest season arrives, wheat fields stretching for dozens of kilometers begin turning their characteristic golden color. High-capacity combine harvesters operate continuously to complete harvesting as quickly as possible, minimizing losses under the desert's extreme temperatures. Thanks to the vast new agricultural land in the Sahara, the new delta has the potential to add approximately 1 to 2 million tons of wheat production per year, about 4 times the wheat output that Toshka once achieved. But Egypt's history includes numerous desert projects that failed because the soil quickly became salinized. This raises a question even more important than production. Can the new delta endure for decades, or is it merely a short-term success? To avoid repeating the failures of the past, New Delta was designed not only to bring water into the desert, but also to control salt accumulation through drainage systems and continuous soil monitoring. In the long run, the project's success will be determined not by how much water is pumped in, but by its ability to preserve soil fertility for decades to come. Egypt is not only trying to grow more food, it is also trying to reduce billions of dollars in agricultural imports. With more than 3,000 hours of sunshine each year, the hot, dry climate of northern Egypt provides ideal conditions for sunflower cultivation. Low humidity helps reduce pests and diseases, while abundant sunlight increases the oil content of the seeds. Beyond supporting domestic cooking oil production, sunflowers also help Egypt reduce its dependence on imported vegetable oils. Every year, the country spends more than $1.5 billion importing edible oils and oilseeds to meet the needs of its population of over 110 million people. With average yields of around 2 to 3 tons of seeds per hectare, and oil content exceeding 40%, each hectare of sunflowers can produce nearly 1 ton of vegetable oil, significantly higher than many traditional crops under arid conditions. This makes sunflowers an ideal choice for the dry lands of the Sahara, where every cubic meter of water must generate the highest possible economic value. While wheat sustains the population at home, Egypt's legendary cotton is grown to compete in some of the world's most premium textile markets. In an industry dominated by massive producers such as China, India, and the United States, Egyptian cotton accounts for less than 1% of global production. What makes this cotton so special is something that is almost impossible to see with the naked eye. Extra-long staple cotton varieties possess fibers that are significantly longer and stronger than those of conventional commercial cotton, allowing the production of premium fabrics renowned worldwide for their softness and durability. But that quality also comes with strict requirements. To preserve the fiber structure, much of this premium cotton must still be harvested carefully to minimize damage during production. Its exceptional value has also made premium cotton one of the most counterfeited products in the world. In 2016, Walmart, Target, and Bed Bath & Beyond were even involved in a controversy after selling products labeled 100% Egyptian cotton that were later found to contain different types of cotton. These controversies only further highlight the unique value of the Egyptian cotton brand. With cotton exports generating more than $500 million annually, and the textile industry contributing nearly $4 billion in revenue, Egyptian cotton remains one of the most important pillars of the country's economy. Beyond crop cultivation, livestock farms, food processing facilities, and logistics hubs have also been developed, while crops such as corn, sugar beets, potatoes, and olives are helping transform the desert into a diversified agricultural hub. The true significance of the new delta may extend far beyond the borders of Egypt. As the global population continues to grow and climate change places increasing pressure on water resources and agricultural land, more and more countries are facing the same urgent question: how can we produce more food with fewer resources? The new delta represents one of the largest real-world attempts to answer that question. Yet the project also comes with enormous challenges. With an estimated cost approaching $10 billion, the new delta depends on a vast water treatment and distribution network that may consume as much as 10 million kilowatt-hours of electricity every day. If successful, a region once defined by sand and rock could become a model for arid nations across the world. But if it fails, it may go down as one of the most expensive agricultural gambles in modern history. Do you think New Delta will be remembered as one of the greatest engineering achievements of the 21st century, or as a costly lesson written in the sands of the Sahara? A machine that can literally mesmerize you, that is the stone burrier. a powerhouse that transforms entire fields filled with rocks into smooth, level soil in the blink of an eye. The working mechanism of the stone burrier is based on a high-speed rotating shaft equipped with sharp blades. As it moves forward, this shaft breaks up the topsoil, crushes and filters it, while pushing stones, weeds, and plant residues deep beneath the surface. On top, only a fine, fluffy, and level soil layer remains, the perfect environment for sowing and planting. This machine is especially popular in Europe, particularly in Italy, Spain, and France, regions with rocky terrain and soils used for vineyards, olive groves, and vegetable cultivation. Beyond Europe, it has also been adopted in high-tech agriculture in Japan and China, as well as in urban landscaping projects across Asia. Picture a giant iron plow carving perfect lines across the field, as if sketching geometry onto the soil itself. This implement is pulled by a tractor, with a large V-shaped metal mold mounted at the back. As it moves forward, the curved wings push soil from both sides toward the center, compressing and shaping it into straight ridges with uniform height and width. This mechanism not only loosens the soil, improves drainage, and maintains moisture around the roots, but also creates the ideal environment for crops that require raised beds such as potatoes, sweet potatoes, sugarcane, corn, and various vegetables. This modern transformer machine is an exceptionally effective solution, designed specifically for orchards and widely used in major fruit-producing countries, such as Brazil, the United States, Spain, Italy, and Australia. Its operating mechanism is based on a powerful spraying system mounted on a massive U-shaped frame with a tank capacity of up to 4,000 liters. As the machine moves along the rows of trees, each spray boom can be adjusted in pressure and angle to release a fine mist that coats the foliage evenly on both sides. The multi-level spray design ensures maximum coverage from the base to the top, reaching even the inner branches that are nearly impossible to treat manually. Thanks to its ability to treat multiple rows simultaneously, the machine's efficiency far surpasses that of smaller tractor-mounted sprayers or handheld units. From that point on, orchards of oranges, apples, mandarins, or grapes no longer have to fear the rapid spread of pests and diseases, as they are cared for evenly, with less time and labor. Of course, owning such advanced technology comes at a price, around $18,000 to $20,000 US. Aeroponic potatoes are one of the greatest breakthroughs in modern agriculture. In this system, the roots and tubers do not grow in soil, but are suspended in the air inside tightly controlled chambers. Ultra-fine nozzles continuously spray nutrient mist directly onto the roots, providing all the water and minerals required. As a result, these seed potatoes are usually ready for harvest after 8 to 10 weeks, which is twice as fast as conventional cultivation. That is why, in a well-managed aeroponic facility, yields can reach 70 to 80 tons of seed potatoes per hectare per cycle, ensuring a stable supply and high quality for commercial production. However, this technology also has some drawbacks. The initial investment cost is very high, requiring misting systems, electricity, and climate-controlled greenhouses. Moreover, the plants depend entirely on the system. Any power outage or technical malfunction can put the entire crop at risk. Despite these challenges, the economic benefits are remarkable. Farmers and enterprises can recover their investment quickly, thanks to the much higher number of seed tubers, while also reducing the risk of diseases compared to conventional cultivation. This is why aeroponics is rapidly expanding in India, China, Kenya, and many European countries, becoming a strategic solution to secure clean seed potatoes and strengthen global food security. So what do you think about this method?